Hi everybody. This is a great day. I get to show you about a couple special right triangles. We'll start off with our friend the 45-45-90 triangle, also known as the isosceles right triangle. It's a pretty simple thing, but a few things to remember once we got a couple things going. Let me just show you about the 45-45-90. I'm going to use the Pythagorean theorem a couple times, but then we'll make some predictions as well. So it begins with this right triangle, as every 45-45-90 must be. It's isosceles right triangle. 5 and 5, and I'm trying to predict that hypotenuse. I'll hit with the Pythagorean theorem. 5 squared plus 5 squared ought to equal the hypotenuse squared. If you see what's coming, that's good. That's 25 plus another 25 equals the hypotenuse squared. And that adds up to 50, doesn't it? Equals the square of the hypotenuse. And taking the square root of both sides, ask yourself that question. You know these perfect squares are going to 50? You say, yes, I do. 25 goes in there twice. And we know the square root of 25 is just 5. So that hypotenuse would be 5 times the square root of 2. Let me lay that right there. 5 times the square root of 2. And I'm recognizing that other isosceles right triangles would be similar to this one. This guy's got a couple lengths of 7s. I'm just going to burn through it. You probably already know the hypotenuse. I'll try to catch up with you. 7 squared plus 7 squared equals the hypotenuse squared. So I got a 49 plus another 49 equals the hypotenuse squared. That's 98. Adds up to the hypotenuse squared. And as I take the square root of both sides, you're probably thinking what I'm thinking. 98's 49 times 2, huh? And I know the square root of 49, so it's just going to be 7. I don't know the square root of 2. I'll leave it in the radical. So this guy's 7 square roots of 2. You figure you know the hypotenuse on this guy? I'm going to verify that for you. 9 squared plus 9 squared equals the hypotenuse squared. Slow it and get it right. 81 plus another 81, huh? Is equal to the hypotenuse squared, and that adds up to 162, but I don't really care about that. As I take the square root of both sides, that's 81 times 2. So that's going to be 9 root 2, isn't it? So you see they're pretty similar. And that's kind of nice, and it makes sense, but it has this little note to go from the leg's length to the length of the hypotenuse in a 45-45-90. I should. What do you do with this length to get that length? What do you do with this length to get that one? I'm going to say I'm going to multiply by the square root of 2. And now we might be thinking, use the Pythagorean theorem to find the missing lengths here, and here I'm given the hypotenuse. When we know the legs, it's pretty easy to come up with the hypotenuse. In fact, you just multiply by the square root of 2. But what if I knew the hypotenuse? What would I do to find out about the legs? And I'm going to go through that motion. You might have an idea already, but we'll talk about a quick and clean way of doing it. But let me just say this is an isosceles right triangle, 45-45. So I'm going to say that those are both x. I'm going to hit with the Pythagorean theorem. X squared plus x squared. I believe you know what those lengths should be. But let's just walk through it and get a good look at it. Equals 6 square roots of 2 squared. And on the left I have 2x squared. And when you square this guy, you're going to square both parts. You'll square the 6 and you get a 36. You square the square root of 2, you get a plain old 2. And 36 times 2, 72. Let's divide both sides by 2, and I got x squared is equal to 36. Take the square root of both sides, and I'm with you. X is equal to 6. That's what you were thinking all along, and I don't doubt it even for a second. Yep, 6 square roots of 2, just like these other triangles. But, now, that was pretty easy. If you have a square root of 2 hanging off the side, to knock it off and get these lengths to each been 6. But what about when it doesn't have that? We ought to talk about that, shouldn't we? I'll call it x, and x is still an isosceles right triangle. We'll find those lengths. There's something I ought to be able to do with that 8 to get these lengths. Now, let's talk about that ahead of time. Then we'll look at it 2 ways. To go from the legs to the hypotenuse, I got to multiply by the square root of 2. Go from the hypotenuse back to the legs. What'd you do with this? Divide by the square root of 2? Could you divide that by the square root of 2? I think you could. If you did divide 8 by the square root of 2, it'd look like that. That's 8 divided by the square root of 2. But the problem is we can't leave it looking that way, not in this class. You can't leave a radical in the denominator of a fraction. This is the good value, but it has bad form. We're going to change the form by multiplying by the number 1. Don't want to change the value, so I'm just going to multiply by 1. And that'll be the square root of 2 which is in the denominator, over itself. Anybody looking have to agree that's equal to 1, and when I do this multiplication, I'm going to get 8 root 2 in the numerator. And in the denominator, the square root of 2 times the square root of 2 is the square root of 4, which is just a 2. So I really get 4 root 2. I'm saying that those will each be 4 root 2, and I'm saying that's really the way to go. But let's go ahead with the Pythagorean theorem. X squared plus x squared is equal to 8 squared. So I got 2x squared is equal to 64. Divide both sides by 2. I got x squared is equal to 32. Take a square root of both sides, and square root of x squared is just going to be x. Now, what do you know about that 32? Well, it is 16 times 2, isn't it? And being as we know the square root of 16 is just 4, we'll call that 4 root 2. And that's an okay way to do it. You might say that's the way I like to do it. But I believe when you work with this a little while, and you recognize to go from the hypotenuse to the congruent sides, you're going to divide by the square root of 2. You'll learn to rationalize the denominator. That's what this is called. When the denominator has a radical in it, it's irrational, the denominator. And when you multiply by the number 1 like this, you have made the denominator become rational. That we have rationalized the denominator there. And you'll see some more of that. Let's figure out what the lengths on this next guy ought to be. I know it's an isosceles right triangle, and I know that these lengths should be the same. And I could hit it with the Pythagorean theorem like I just did. But let me make a prediction with you. To go from the legs to the hypotenuse in a 45, 45, 90, I multiply times the square root of 2. To go from the hypotenuse back to the legs, I got to divide by the square root of 2. And if you took 10 and divided by the square root of 2, it's going to look like that. And that's good. That's the right value. That's how big these would be. But when you type that on a calculator, it'd be just fine. I feel like doing that, but I'm not going to. I'm going to rationalize the denominator instead. Rationalize the denominator, you say, yeah, right now the denominator is irrational. The square root of 2 is irrational. It's a non-terminating, non-repeating decimal. We need to get rid of it from the denominator. I don't want to change the value, though, so let's multiply by the number 1. The square root of 2 over the square root of 2, which would give me 10 root 2 over a plain old 2. So those lengths are going to be 5 times the square root of 2. And I don't doubt that you knew that ahead of time. That's okay with me. 5 root 2 for each of those. This length would have been the same, huh? I'm going to hit it with the Pythagorean theorem. We're going to verify that one more time. X squared plus x squared is equal to 10 squared. 2x squared is equal to 100. Divide both sides by 2. X squared itself is equal to 50. Taking the square root of both sides, square root of x squared just x. What about that 50? Well, it's 25 times 2. I know the square root of 25, so it's 5 root 2. This is going to be a lot quicker way to go. And we can get the lengths of the legs pretty quickly that way. So these were each 4 square roots of 2, and these were 5 square roots of 2, and we can do that. I just got a little note for us to pay attention to. To go from the length of the hypotenuse to the length of the legs in a 45, 45, 90, and going in that direction, we're going to divide by the square root of 2. Divide by the square root of 2. But when you divide by the square root of 2, chances are good you will need to rationalize your denominator. Just for a little look, what's 12 divided by the square root of 2? And once you work on that for a second, I can turn the computer off and you can think about that, but it's going to be 6 square roots of 2. Real quick, real easy. You'll get used to doing that nicely. Then there's a couple of questions on the bottom of the page. We're just going to touch a couple of bases. Looking at this triangle, I guess use the axioms from above to find the missing links in these isosceles right triangles. We're told ahead of time they're isosceles, and 3 and 3, I guess this is 3 square roots of 2. Going from the leg to the hypotenuse, I multiply by the square root of 2. This is more interesting, isn't it? Here I got a 45, 45, 90, but the hypotenuse is 1. How big are these going to be? Well, to go from the hypotenuse to the legs, I got to divide by the square root of 2. I'll take the number 1 and divide it by the square root of 2. And there it is right there. That's how long these legs should be. Just don't turn an answer in looking like that. You should rationalize the denominator. Right now it's irrational. We don't want to change the value. Let's just multiply by 1. The square root of 2 over the square root of 2. And 1 times the square root of 2 is just that, the square root of 2. Square root of 2 times the square root of 2 is just a plain old 2. So what we got is the square root of 2 over 2. The square root of 2 over 2 is about 1.414 over 2, which is about 0.707. But let's leave it this way. This is the square root of 2 over 2. That's what these each would have been. Square root of 2 over 2 on each of those lengths. There's a really cheap one right here. I'm not sure why I wrote this question. I think there's other things going on here. Let me go back here. This one, it asks for the perimeter of triangle PQR. A little thought there. The perimeter, there would be, well, there's some sides I can add up. That's 6. I can add up a couple of 3's, plus 3 square roots of 2. This is a rational number. This is an irrational group. And we're going to keep them separated. That's how you should write that perimeter. Here we knew that AB and BC were congruent, and they were each the square root of 2 over 2. And there's a kind of a good question here. If this length is 11 and this length is 11 square roots of 2, if you use the Pythagorean theorem here, I know that you would find this to be 11 as well. And the measure of angle A, under this circumstance, it would have had been 45, huh? It's a 45, 45, 90. And the perimeter of the triangle, you add them up. 22 plus 11 square roots of 2. That's a pretty nice triangle, and it's good for you to know about the 45, 45, 90. But my real buddy today, the guy we're going to care the most about, is the 30, 60, 90. Probably a little more important than the 45, 45, 90, but they're going to show up all over the place. I would say this, the 45, 45, 90, where would you most often find him? In a square. That's for sure. Anytime you got a square, all the sides are going to be congruent. You show a diagonal, then you get built with a 45, 45, 90 right there. That's just a place to expect a 45, 45, 90 is in a square. But let's look at this 30, 60, 90 triangle. Find some places we can deal with him too. Consider the 30, 60, 90 triangle at right. Let the shorter leg of the triangle be 1 unit. And I'm going to allow this to be the 30-degree angle and this the 60. Looks that away, and here's the 90. And if opposite the smallest angle, we'd find the smallest side. I'm going to call that length 1. And knowing that, I'm going to be able to figure out these other links. Let me show you something I think is a little bit clever. I'm going to cut that angle right there. Not going to bisect it. It's a 90. I'm going to let this part be 60 and this part be 30. I just whack that angle into a couple of congruent parts. Not congruent, into a couple of parts. But if I make this part be 60 and this part be 30, look at this triangle first, above triangle. That one's 60 and that one's 60. This one would have been 62, wouldn't it? 60 also, wouldn't it? So, if this side were 1 and this is an equiangular triangle, therefore an equilateral triangle, this would have also been 1. And this would have also been 1. But, looking further, what about this triangle at the bottom here, the one I'm going around now? It's got a 30 here and a 30 there, doesn't it? So this darn thing's isosceles, huh? And since this length was 1, this length has to be 1. I'm thinking the hypotenuse is 2. What about you? Think so? Yeah. A thing to remember. We're not going to draw this all the time, but what we're going to remember from it is the short side opposite the 30 always doubles to become the hypotenuse. And this is the reason why. But now, let's find out about this length right there. When we work through 30, 60, 90 triangles, I'll call the opposite the 30, the short side, opposite the 60, the longer leg, the longer side, and the hypotenuse opposite the 90. I'm just going to call that the hypotenuse. Let's go for this length right there. I'm going to call it X. That is the longer leg opposite the 60. That basically going to be pretty simple numbers with the Pythagorean theorem, but let's see what happens. 1 squared plus x squared equals 2 squared. I can do this. 1 plus x squared is equal to 4. Subtract 1 from both sides, and I'm thinking that x squared is equal to 3. I want to know about x itself, so I'll take the square root of both sides, and x is the square root of 3. Now, that worked really nicely here. I kind of feel like taking all this junk away, and I'm just going to show you a nice clean 30, 60, 90. With a 60 here, and a 30 there, and a 90 here. Short side's 1, hypotenuse is 2, the longer leg is the short side times the square root of 3. 1, 2, square root of 3. Those are some numbers you're going to put together with the 30, 60, 90. But, okay, we're going to walk through this thing, and then we're going to come up with some rules at the end. Hey, this is a 30, 60, 90, isn't it? And this side is 12. So I'm asking myself, what do you do to go from the hypotenuse to the short side of a 30, 60, 90 triangle? In fact, you take 1/2 of that length. This would have to be 1/2 of that length. It would have been 6. And now I'd like to go from the short side to the longer side opposite the 60. I'm going from the short side opposite the 30 to the longer side opposite the 60. And what do you do with this length to make it become that one? I had to multiply that by the square root of 3 to become this length. So this length would be 6 times the square root of 3. So AB is 6 and AC is 6 square roots of 3. You hit that with the Pythagorean theorem, it's going to work out beautifully, I promise you. Let's go again. This time, I know this side, that's 5, and this is a 60, there's a 30, there's a 90. This must be the 30 up here, huh? So in fact, that's the short leg, isn't it? How are you going to go from the short side to the hypotenuse? Well, I'm going to double it. This would have to have been 10. So FD is 10. But what about this side? And I would tell you, well, that side's opposite the 60. That's what we call the longer leg. And what does one do to go from the short leg to the longer leg? What does one do to go from the short leg to the longer leg? You've got to multiply this length times the square root of 3. That is 1 times the square root of 3. So here, if that's a 5, I'm going to have to call this one 5 times the square root of 3. That works pretty well for that triangle. And they're kind of similar, aren't they? 5 root 3 and 10, 6 root 3 and 12. Interestingly here, though, we're given the hypotenuse, aren't we? I'd say if I know the hypotenuse, and this is a 60, then this must be a 30. So here's our short side, and the short side opposite the 30 is always 1/2 the hypotenuse. Therefore, this would have had to have been 12. I'd like to know this other side over there if I could. That's opposite the 60. That's the longer leg. What do you do to get from the short leg to the longer leg in a 30, 60, 90 triangle? What do you do with this number to make it become that number? You got to multiply it by the square root of 3. So this would have been 12 root 3. And I'll write those numbers over there too. HJ was 12 root 3. 12 root 3. And JI is just 12. And let's play some more. Now, here's about to get interesting. Here's the 30, 60, 90 triangle. There's the 90, here's the 30, here's the 60. So, what side do we know about the 30, 60? I'm going to say something dumb. I think 30, 60, 90 triangles are a lot like life. You say, well, how can that be? Well, in life, you got to figure, where am I now? Where do I want to go, and how do I get there from here? In this triangle, you got to think, where am I now? What side is this? Well, it's opposite the 60. That's the longer leg, isn't it? Where do you want to go? Well, how do you go from the longer leg to the shorter leg? What do you do from the longer leg to the shorter leg? You got to divide by the square root of 3, huh? This length divided by the square root of 3 would give me this one. So we got to take that length and divide it by the square root of 3. And that would give us the shorter length. It would just be 12. And then I wish I knew the hypotenuse. So if I think about this triangle, what is it? Every 30, 60, 90 triangle is going to be similar to this one. What do you do to get that hypotenuse if you know the short side? You double the short side to get the hypotenuse, don't you? So if I double you double the short side to get the hypotenuse, don't you? So if I double the short side to get that hypotenuse, it'd have to be 24. So LM is 12 and KM is 24. Put them on the picture, works just as well for me. Here it's going to get a little more interesting. Look at this. We still got a 30, 60, 90 triangle. There's a 30, a 60, and a 90, and that 12. Not the hypotenuse, that's the short side, or what? Is opposite the 60. That is the longer leg. I have to ask myself, well, how can I get to the shorter leg? What do you do with the longer leg to get to the shorter leg? What do you do with the longer leg to get to the shorter leg? I got to divide by the square root of 3. Now, if it had a square root of 3 hanging off of it, it'd be easy to knock it off and divide by the square root of 3. But what if we just have the number 12, which is the longer leg, and I wish I knew the shorter leg? I know I got to divide it by the square root of 3. Should we leave the answer looking like that? No, you can. Not in this class. I mean, minus 3 if you do. This is the good value. It is 12 divided by the square root of 3, but we can't leave that radical in the denominator. I don't want to change the value, so let's multiply by the number 1. What would it be this time? As you rationalize this denominator, you're going to multiply by the square root of 3 over the square root of 3, which would give us, watching carefully, 12 root 3 over 3. Just the square root of 9, which is 3. Yeah, we can reduce that, can't we? It's going to become 4 times the square root of 3. Oh, I think I just figured out the short side on this triangle right there. Go from the longer leg to the shorter leg. I divide it by the square root of 3, multiply by the number 1, and come up with this value there. So, this length is 4 root 3. If I could just figure out the hypotenuse. What do you know? How can you get to the hypotenuse here? Because this triangle is going to be similar to that one. I should double the short side to get to the hypotenuse. Who's the short side? 4 root 3. So what would be the length of our hypotenuse? It's going to be 8 times the square root of 3. I'm not going to worry about writing those lengths there, but there we have that one. This was quite the same. If I was you, I'd shut this down and work this out before I tell you those answers. That's 15. Opposite the 60, isn't it? That's a 90, that's a 60, this must be a 30. This is a 30, 60, 90 triangle. Where am I now? Where do you want to go? How are you going to get there from here? I'm at the longer leg. I wish I knew the shorter leg. To go from the longer leg to the shorter leg, I got to divide by the square root of 3. Let's take the number 15 and divide it by the square root of 3. Can't leave it looking like that. Some of you already know what this is going to become, and that's clever. I do too, but let's go ahead and go through the motions. We should get that radical out of the denominator. It is irrational at this point. Multiply by the number 1, square root of 3 over square root of 3, which gives me 15 root 3 over plain old 3. Square root of 3 times the square root of 3 is the square root of 9, and that's just 3. Yeah, we ought to call that 5 root 3, shouldn't we? So that would have been the short side on this triangle right there. 5 times the square root of 3. If you wanted the hypotenuse, and I figure we do, we have to double the short side. The hypotenuse, RS is 10 root 3. Yeah, I'll put them there, but that's not what's important. QR was 5 root 3. Okay. The bottom line on the 30, 60, 90 triangle, to make these movements, let's put some numbers on this guy right here. And I'd say the simplest 30, 60, 90 triangle in the world has a short side of 1. The hypotenuse is 2, and the longer leg is the square root of 3. Same fellow that we looked at up here. Working from him, you could do a lot of good mathematics. To move from the short leg to the hypotenuse, to go from this length, opposite the 30, to the hypotenuse, you multiply by 2. Multiply by 2. To go from the hypotenuse back to the shorter leg, I guess I got to do the inverse of that. I'm going to divide by 2. To go from the hypotenuse back to the shorter leg, yeah. What do you do with that number to make it this one? I'll divide by 2. From the short leg to the longer leg, from the short side here to the longer one there, what do you do with this number to make it become that number? I got to multiply by the square root of 3. Multiply by the square root of 3 there. And kind of conversely, to go from the longer leg back to the short leg, if I knew the longer leg and I wished I knew the shorter leg, what do you do with this number to make it become that one? You got to divide it by the square root of 3. All 30, 60, 90 triangles will be in the ratio that these exhibit. So remember that.